My name is Kenneth Wright. I'm Senior Director in Rambus Labs, research arm of Rambus. Recently a new OpenPOWER OpenCAPI member. I'm here to talk to you today about hybrid memory platform and research into emerging memories that we are developing for the OpenCAPI and Power9 systems. As an outline, I'd like to start with giving you a bit of background or the opportunity that we see in memory subsystem design going forward. Then a little bit of the research that we've been carrying on in the hybrid memory arena for the last couple of years, including some results of our simulation environment. Then I'd like to talk to you about our hardware platform that we are building and seeking collaboration on that is used to evaluate some of the management schemes that we've developed through simulation, and then talk a little bit about the collaboration itself. So we start with the opportunity, and this is kind of the memories version of the Moore's Law graph. I originally had pulled it from my slides, but I saw that everyone was using it, so I said, okay, I'll put it back in. So this is showing the driving factor in memory, which is really has capacity for a given investment, how it has decreased over time. Basically, it's saying bits in the future are always cost less than bits today. And as we continue to see capacity increasing, the demand for capacity increasing, we also see the slowing of this curve, especially around DRAM, which is our primarily memory component in a memory subsystem nowadays. And then we're starting to also see here a bit of NAND flash, which is kind of the highest speed storage component. So when I talk about memory, I'm really talking about things that have load store access out to or out from the processor. When I talk about storage, I talk about something that's generally paged in or isn't directly accessed through a load store model. And the cost gap between the two is continuing to grow. That everyone knows. But also both curves are continuing to flatten and not accelerate the capacity growth like we're used to for the same investment. So it has been talked about for a long time that emerging memories, the new memories on the market, will come in and help fill this gap. But those have had to struggle. They're still emerging into the memory subsystem, although some of them have emerged into the storage subsystem. So we see a lot of big opportunities in the memory subsystem, and I think that this is, shown by the amount of disruption that's presently going on in the modern memory subsystems. This level of disruption hasn't been seen in decades. We're seeing new attachment strategies, new ways of attaching memory into the central processing unit, right? OpenCAPI, Gen Z, CCIX are all proposed as ways that in the future we'll be able to attach memory to our systems. We're seeing extensions of the standard DRAM or DIMM protocols and things like transactional aspects. We're also seeing new module architectures. People are beginning to talk about differential DIMM, using differential signaling out to a DIMM, or non-volatile DIMMs like NVDIMM-N, which has had some deployments already in hyperscale systems. NVDIMM-P, a fundamentally similar technique where both DRAM and flash, a technology that is very much emerged in the storage but has yet to emerge in memory, are being combined onto one module. And all the different memory types that we're seeing, all the different ways of storing bits, various types of resistive RAM or RRAM, various types of magnetic RAM including spin torque memory, PCM memory, and now we're seeing the emergence of ultra high speed, ultra low latency flash that looks like it would be a good candidate for the memory subsystem. But none of these technologies have a directly supplant DRAM. You have DRAM, which has incredibly low latency. Hardware latency is 30 nanoseconds or so. almost infinite endurance. Wright energy, because charge is being stored, is very low. It's very manufacturable, although some people might argue with that now that we have super towers of capacitors and things like this. But it is proven to be and continues to be very manufacturable and has quite good capacity. None of the other technologies that are coming to the forefront completely replace this. Flash, even high-speed flash, is very manufacturable and has been shown to scale quite well, has better capacity than DRAM, but its latency is not as good, especially around writes. Its endurance has to be managed very carefully. And its write energy can be in a comparable level. If you go across the chart, you see that none of these memories will completely supplant DRAM. And matter of fact, it's my belief that a hybridization of DRAM and an emerging memory is where the future lies. And this is something that we kind of rallied around a couple of years ago and said, if this is the way that we will eventually be building memory subsystems, someone needs to go out into the forefront and start trying these things. Try the hybridization and see what the right ratios are, the right algorithms, management schemes. You know, in memory, in many ways, we've had a hybrid memory subsystem forever. The very first memory subsystem that I remember reading about was all SRAM. It was a Cray system, and he loved SRAM so much he made his entire memory out of it, right? SRAM is still in our memory subsystem. It makes up our caches. DRAM never fully supplanted it. And I believe that these emerging memory technologies will go that same way. You'll never see them fully supplant DRAM. There will be a hybridization in the stack. So when we started this research, we had a simple goal: investigate memory subsystem architectures and attachment strategies of the future. Specifically, multiple memory types in a memory subsystem. Not just DRAM, but a memory subsystem consisting of DRAM with one of the emerging memory technologies. Also to investigate multiple different attachment schemes, serially attached, direct attach, and other things. But it very quickly became obvious that the management techniques were the thing that was either going to make or break this type of memory subsystem. How do you manage the endurance? How do you manage the latency? How do you manage the bandwidth of your emerging memory? And how do you use your DRAM effectively to do that management? So, going forward, we're wanting to create a collaborative ecosystem of academic and industry partners to develop a prototyping system where we can all experiment in these management areas and get very rapid and very collaborative designs to go forward, okay? But I'm getting a bit ahead of myself. Let me talk a little bit about the tracks of research that we've been performing and the way we see this evolving. We see three primary tracks: performance modeling or simulation, hardware prototyping, and management, both in software and hardware. Performance modeling we've been doing for approximately 2 years on a Gem 5 based system, and we've seen some very promising results. But like any simulation, it has some challenges. First, compared to actual hardware, it's quite slow. And it takes a long time to run any sizable benchmark. And many benchmarks are just intractable in simulation. So it also limits the number of scenarios we can run because of the speed and, you know, the shortness of our lifespan. Then we also, the most troubling for me is the simulation assumptions. Anytime you build a simulation engine, there are certain assumptions that are sometimes not even in your forefront of your consciousness that you make when building it, that may not be validated when you move to real hardware. So we're now ready to move into the next stage and the next track. Not that the first track is going to stop, but the next track is taking some of the management techniques that we've developed and implementing them in actual hardware. So we can run full benchmarks on a custom board with real Power 9 and OpenCAPI interfaces. So that is the stage that we're moving into now. We are also continuing our work on software and hardware management schemes. I've been calling, when a memory subsystem is managed by hardware, I've been calling it hybrid memory. And many of the academics are starting to pick up on this. When it's managed by software and it's exposed where data placement and data migration is done by software, I call it heterogeneous. So you'll hear me use those two terms in the presentation. But in general, something needs to manage data placement and data movement between the different memory types. Okay, so I'm going to show a little bit of our simulation results, which I find very promising, and it's one reason that we're so excited about moving forward. It takes a few minutes to completely walk through this so you get the gist of what the simulation is saying. So we've done detailed simulations where we've looked at both read performance, bandwidth and latency, write performance, endurance, hybrid capacity ratios, you'll see what I mean by that in a minute, and different attributes of the emerging memory. So let me tell you how to read the chart on the left. We have various workloads. This is a small sample of the workloads we've run in simulation. And we suppose a memory subsystem. In this particular case, we supposed a 1 terabyte memory subsystem. And we said if we made that out of all DRAM and ran the workload, we'll call that 1 as our reference point. That is basically execution time. But there may be many reasons why a terabyte memory subsystem of all DRAM may not be tractable, either because of power, space concerns, cost, many things. So we also suppose that you make the same memory subsystem as a terabyte out of an emerging memory. This particular emerging memory we chose had a 3 microsecond read and 100 microsecond write time. So with no management at all, just taking the benchmark and running it against the emerging memory, only managing for endurance, these are the numbers you get. You can see that some of these are 100x what a DRAM solution would be. Obviously, this isn't something that makes a lot of sense to go forward, right? This greatly impacts system performance. Now, we take the same emerging memory, but we make the memory subsystem this time 1/16 DRAM and 15/16 emerging memory. We apply some management schemes, both in software and hardware. Software giving hints about data placement and data movement to hardware, and hardware doing the nanosecond level real-time implementation of that policy. And as you see, we can get very close to an all DRAM solution, which I find uniquely impressive. We've taken something that is in the microsecond time scale with a very modest amount of something that's in the nanosecond time scale and gotten very close to the same performance. This could have many benefits: lower energy, lower cost, more density. So many techniques were used to get to these numbers. And the nice thing about simulation is we can kind of do an if-then kind of test. One of the interesting things that we did was we recognized that writes stalled behind reads could be a big problem. So these results show us using what's called interruptible writes in the emerging memory. Now, we have some circuitry that we have supposed that could be built into many emerging memories that allow this. But just from a performance simulation, I'll show you how this if-then kind of experiments can be run. So we say, okay, let's just take the data from previous. You'll notice that is in your far right-hand column. And the far right-hand column is with the interruptible writes, same data that was on the previous chart. Now, if we back out that one assumption and we say the writes in a particular emerging memory aren't interruptible, Once you start a write, if a read comes in, you have to finish the write before the read can be done. And you can see that in many cases, it's almost a 1x kind of addition. So these types of attributes are very important, and many of them swing things much larger than this. So the simulation has led us toward management techniques on various different emerging memories that we now are beginning to be ready to implement in actual hardware. So, we are in the process of developing a modular and flexible hardware platform. This is specifically for research in this area. The idea is that you can mix and match any of the interface controllers and interfaces. So you'd have an FPGA platform that implements the hardware management policies. You would have an interface controller that talks to the processor. That interface controller is completely modularized, and the way the hardware management policy engine talks to it is in a generic way. On the other side, you have DRAM controllers and emerging memory controllers, once again with abstracted interfaces so they can be switched out. And then you would have the memory subsystem itself, or the memory, the hybrid memory. Now this is the goal, but we'll have a first instance of it. And in the first instance, the initial platform we're developing, we're going to take the IBM P9 server. We're in joint development with IBM to create this research platform, and we're hoping to be able to demo it by the end of the year. We'll have memory interfaces that will allow low latency access through OpenCAPI. That was really the reason we were very excited to partner with IBM. There is nothing else out there that will allow this type of research to be done at latency time scales that make sense for a memory subsystem. And we're still looking for emerging memory collaborators. We are in discussion with several of the large emerging memory producers, and some of them are starting to work with us already. So, this is what our initial will look like. It's just now going in to layout, so I don't have a layout diagram, but we're hoping to have it, as I said, by the end of the year. We'll be using the low latency OpenCAPI, which is on the right of the diagram, and possibly other interfaces that we're putting on the left side of the card. It draws its power from PCIe, and it will support many different memory types. First, it has DDR4 DIMM slots, so standard DDR4, both DRAM, NVDIMM-N, that's a tongue twister, and NVDIMM-P support. We will also be able to make custom DIMMs out of various emerging memory types and even enhance flash custom DIMMs. It has one emerging memory slot itself, which uses a standard DIMM connector, but is a little further away from the FPGA and will be used for lower bandwidth and lower signal integrity intensive applications. But with this platform, you can have DRAM and flash, DRAM and PCM, DRAM and whatever. You could even have two different emerging memories. Let's say STT-MRAM and another emerging memory like high-speed flash, and start really seeing how the management policies work in full-blown benchmarks. So, see, how am I running on time? Oh, not bad. So, research opportunities and partners. So, the Rambus, in Rambus, we are working to provide this platform, and we're looking for collaborators who want to work on this platform with us. We're hoping to do benchmarking and develop various management policies. We're aligning ourselves with IBM as a processor leader who is interested in programming models, resource sharing and partitioning and provisioning, and interface comparisons. So we'll be able to do various comparisons of different interfaces going out to the emerging memories. We're engaging with memory leaders in hopes that they'll be able to use the platform for analysis of the emerging memories that are coming out, such as PCM and others. Demos, this may be one of the first places that you'll be able to take an NVDIM-P and run real server workloads on it, and do real application testing. We're also hoping to partner with system vendors who may one day want to take a version of this into actual production to produce the real next generation emerging memory, hybridization. So we're interested in collaboration, and please see me afterwards if you'd like to talk more about this. So I sped through that very quickly and didn't take any questions or any comments, and I was hoping to have a few. Otherwise, we're going to all get to go to coffee a little early, but we can take them now. Yes, it's quite impressive. So the DRAM in this case, let me go back one more. The DRAM in this case was a multi-channel, it was 4-channel simulation. We have simulations of various and different structures. It was 4 channels of DRAM running at 2400 DDR4. Standard 2400 latency numbers, right out of JEDEC specs. Order, you know, it depends on if you get a page hit or you get a bank conflict or something like that. But with a page hit, 30 nanoseconds-ish, pin to pin on the DRAM, 80 nanoseconds load to use to the processor, something in that range. And this is, as you see, the 3 microseconds was pin to pin on the emerging memory. It wasn't load to use, but when you're talking 3 microseconds, the extra cache levels is kind of in the noise. Yes, please.
Just a statement. This reminds me of some work when the hard drive guys were trying to get more oomph out of their drives, and they used a little bit of RAM, probably 1/16 less in terms of capacity, and they got tremendous results out of RAM caching of hard drives.
Mm-hmm.
So,
The management techniques here, I would not necessarily classify as caching, because there's definitely some other things going on. Because caches don't have this idea of endurance management. They also don't have this idea of block management. So it's a little bit beyond what you would learn in a standard caching algorithm. It's kind of rotational wear leveling mixed with caching, mixed with prefetching, and some very interesting synergies develop when you start actually studying it. No. But they are access pattern dependent. And one of the things that we are doing research on is learning access patterns, and that's what I was talking about, where the software can give hints to the hardware to change data placement and data movement policy to depending on what the use pattern is going to be. And we're also working on a framework where that is learned automatically. And it's just the access and the allocation is analyzed and fed to the hardware slightly beforehand. So we know what your allocation patterns are, and from that we're inferring your data use patterns via using some AI and feeding that down to the hardware. Didn't want to quite get into all that unless I got a question. That's why I didn't put it in the slide deck, and they made me promise I would not go over time. Please, any other questions? I think we have the room until when? 30 minutes, another 4 or 5 minutes. Any other questions? Please.
The ratio between RAM and emerging memory, have you played with this? Apparently, we're going for capacity as well as latency, right?
So
1 to 100 would be another metric.
So we have varied it, and we have a paper that we are submitting later in the year. We have varied it from 1 to 2, which is kind of odd, all the way to 1 to 64, and seeing different benchmarks and different workloads have different sensitivities to that ratio. 1 to 16 works on these benchmarks very well, but even if you go to 1 to 32, it's surprisingly how little you lose. But, you know, I can't show all the results all at once. But we'll have a paper we're hoping to have in MIMSIS that's later in the year that will have a lot more variation on the ratio. The ratio is, you know, remarkably interesting what ratios work well. So, I'm sorry, there was a question over here also?
So, you guys don't make memory, right? So, this is a system design? Is this a partner, like an FPGA partner helping you with this? Or what's the total?
Yeah, there's a lot of partners that are going to end up helping us with this. We just put out the press release this morning, actually, for our partnership with IBM. So we're definitely we're working with partners on the emerging memory side, on the DRAM side, and the FPGA side. And we're getting all that where we can make various announcements about it, but wasn't quite ready to do all those announcements for today. But yes, this is a collaborative environment. We're more interested in the algorithms, things like the ratios, how these hints can be passed between hardware and software. That's, you know, our research. In reality, we're building the platform to kind of validate some of the things we're seeing in simulation. But the platform, I think, will be super useful to a lot of different people. Like today, it is speculated that there are several people who have NVDIMM-P modules that they could show even now. But there's no system that uses NVDIMM-P yet. So a system like this could be used for demonstrations and benchmarking and things like that. And the fact that you have such a low latency access from the processor and eventually a load store access, not a DMA access, a load from the processor targets the memory subsystem out on OpenCAPI and comes back. That's kind of the holy grail of getting this to work correctly and showing these kind of performance numbers. Let's see, we have 30 seconds if anyone else has anything. If not, I'll be around afterwards and I'll be happy to talk to you. Thank you very much for your attention.